So good morning. Thanks for having me to talk again this year. I visited last year as well. And last year I told you about studying gamma ray astrophysics with Veritas. Very high energy gamma rays, or particles with an enormous amount of energy, much more than, say, the total energy in a proton or a neutron. So this year I'm going to recap that a little bit and remind you a little bit how Veritas works to detect gamma rays just for a couple minutes. And then I'm going to talk about looking for dark matter, why we think, what dark matter is, why we think it exists, and how you can look for it both with Veritas and other techniques. So a number of the slides that I'm going to use today were actually produced by my postdoctoral associate, Daniel Nieto, so I wanted to give him credit as well for this work. Okay, so what kind of telescope detects gamma rays? Well, gamma rays are the high energy end of the electromagnetic spectrum. They're more energetic than X-rays. So they don't actually get through the atmosphere. The atmosphere is not transparent to gamma rays. Instead, when a gamma ray enters the atmosphere, it tends to interact and create electron-positron pairs and other gamma rays. So we don't use a telescope to detect the gamma ray itself. Instead, what we do is we look at the radiation produced by this little shower of particles that a gamma ray makes. We collect that radiation and infer information about the gamma ray from that information. So the kind of telescope we use is a large optical dish. This is a Veritas telescope. This is one of 4 Veritas telescopes. This is the project I work on primarily. And these optical dishes are 12 meters in diameter, so 100 square meters of glass, collecting light and focusing it onto a camera. So yeah. So this, I think these slides came a little bit out of order. I would have preferred to show this one first. Just to remind you of the electromagnetic spectrum, where radio is at the longest wavelengths, and then infrared, the optical band, ultraviolet X-rays, and then gamma rays is everything above X-rays, just like radio is everything below infrared. And so optical photons have an energy typically of a few or 10 electron volts. That's an energy unit, electron volt, that we like to use in particle physics and astrophysics. Don't have to worry this morning about exactly what an electron volt is, but gamma rays, just to set the scale, have energies of millions to billions to trillions of electron volts. So they're a million to a trillion times more energetic than optical photons. So that's part of what makes them very interesting for us. That it takes really special processes in the universe to generate gamma rays. So they're very special compared to optical photons. We like to study those. So, as I started to describe, when a gamma ray is generated by some powerful astrophysical object, it goes through interstellar space, and then when it reaches our atmosphere, it interacts and creates a shower of particles, mostly electrons and positrons. And some of those particles will create something called Cherenkov radiation. This is a form of radiation that's effectively an electromagnetic shock wave. And it's largely blue light and ultraviolet light. So we don't see the gamma ray itself. It turns into all this shower of particles. But we do detect this Cherenkov radiation by using these large optical reflectors. And so we image this Cherenkov light that's produced from particles all along this shower's development. And so we collect that light and create an image of an air shower in our camera, and use that image of the air shower to reconstruct the direction and energy of the primary gamma ray. So there's the Veritas telescope again, 100 square meters of mirror area. There's a trailer that sits next to it with the electronics to read out the camera and provide power to the telescope. The camera looks like this. It's a 3.5 degree field of view camera, so it's a very small field of view. It looks at a small patch of sky at any one time. and it has only 499 pixels. So not nearly the kind of resolution that you get from an optical telescope or a digital camera on your cell phone. So this camera, in a little more detail, it takes very fast snapshots of what the sky looks like. So a commercial digital camera might have 5 million pixels and cost $200. This one, it costs $500,000 to give you 500 pixels. And the difference is that where your commercial digital camera is read out by a CCD chip, which is very cheap and easy to produce, and integrates light over milliseconds or seconds even if you're looking at something dark. In this case, the camera is made up of photomultiplier tubes. So these are devices that are able to detect individual photons, individual particles of light. So they're very sensitive photodetectors, and they can operate on very fast signals. So we take images that are only 10 or 20 nanoseconds long instead of a second. So that's what makes it so expensive. What the data looks like is like this. So this is an example of an air shower that provides an image in each of our 4 telescopes. And so those images look roughly elliptical. The stars are meant to represent where on the sky or where in the camera the gamma ray was originally coming from. And you can see that the images look like ellipses roughly that are all pointing back roughly towards that star. And so that's how we can actually use information from these images to reconstruct the direction of the gamma ray. These telescopes all look at the same patch of sky. So if you look at the direction of these ellipses and look at where those directions intersect on the sky, they all intersect near the star location. And we can play a similar trick to see where the gamma ray would land on the ground by looking at the telescope positions and the directions of the ellipses and seeing where they intersect, find the position on the ground. And that tells us how far the gamma ray, how far away from the telescopes the air shower develops. And so that distance coupled with the total amount of signal we see in each image gives us a way of estimating the energy of the gamma ray. The further away the air shower is, typically the less light we see for a given energy for the gamma ray. Okay, so that's a really quick overview of how we get the direction and energy of the gamma rays. And now I'm going to move on to the main thrust of today's talk on the role of dark matter in cosmology and how we can go about detecting it. So cosmology is the subfield of physics and sets out to describe the history and the large-scale structure and dynamics of our universe. And in the last 15 years, we've seen amazing progress in quantifying the constituents of the universe, the types of things that make up the energy budget in the universe, and the basic evolution, the basic history. However, what we found in doing that is that 95% of the universe's content is completely unknown. So the things we know about are atoms, protons, neutrons, electrons, and related particles that all fall in the standard model of particle physics. And they make up about 4.5% of what's in the universe. And the rest falls into 2 large categories. Dark matter is what I'll talk about today. That's about 23%. That seems like some other kind of matter, some kind of particle that's different from the particles that we're familiar with every day. So it has different kinds of interactions. In particular, it does not have an electric charge, so it doesn't respond to electricity and magnetism. But there's not much more we know about it than that. And then the other major component is called dark energy. That makes up about 3/4 of the energy in the universe. And this is, so far we don't really ascribe any kind of particle to the dark energy. It just seems to be something that's growing in importance as the universe gets older and is driving the expansion of the universe. Where 20 years ago people thought the universe was expanding, but presumably gravity was slowing down the expansion of the universe. What they discovered by looking at supernovae at different distances away from us is that it looks like the expansion of the universe is actually getting faster with time rather than slowing down. So there has to be some other force acting on large scales in the universe to drive that expansion and counteract gravity and actually overcome gravity. And so we call that force dark energy. But again, it otherwise remains fairly mysterious. We don't know a whole lot more about it. So I'm going to focus on dark matter. This is something that we can address with gamma rays. I'm going to talk a little bit about the evidence for the existence of dark matter and some possibilities of what it can be made of, and then how we can detect dark matter. So the evidence, it comes in a few different forms, largely from various astrophysical observations. Dark matter, in putting together the standard cosmological model, and understanding data measured from the cosmic microwave background, and the abundance of different elements and different isotopes of elements that were generated shortly after the Big Bang, and in understanding how structure forms in the galaxy, in the universe. So stars forming, galaxies forming from clusters of stars, clusters of galaxies forming superclusters. How all that works together seems to require the presence of dark matter. And then the internal dynamics of galaxies and galaxy clusters also appears to require dark matter. I'll talk about that a little bit. As well as something called gravitational lensing, where the path of light gets bent by gravity, seems to require dark matter. So I'm going to focus more on the dynamics of the galaxies and the galaxy clusters and the gravitational lensing. So back in 1933, Frederick Zwicky found a little problem in some measurements he made. He was looking at the nearby galaxies in the Coma cluster of galaxies, and looking at how they were, their motions around their common center of mass. And he found that the velocities of the galaxies required that the mass of the entire system had to be 10 times higher than what you would estimate if you just looked at the starlight. So that was a little deficit. And then that was more lately confirmed in other galaxies. So it seemed to imply that the luminous matter, the stars, did not trace the total mass of these galaxies, and that there had to be some substantial component of dark matter that wasn't being accounted for. So what's going on there is that if you use Newton's laws, which for galactic dynamics is largely good enough, you can estimate the velocity of stars or of galaxies in a system by relating to the radius from the center of the system and the mass enclosed inside of that radius. And what you find is that if you're inside some distribution of matter, roughly speaking, the velocity should grow faster as you go out along your radii. But as you get outside of the distribution of matter, so if most of the matter is inside of your radius, then the velocity should start to drop off slowly with radius. And so this plot over here shows velocity as a function of radius from the center of the galaxy. And this curve labeled visible matter, you see it rises rapidly at small radii and then drops off slowly at larger radii. That's what people expected using Newton's laws and the assumption that all the mass is represented by stars. So we could estimate the mass enclosed in some radius from the starlight. These data points here are actual measurements of